Okay, so section 6.1 deals with exponential functions, okay, exponential functions. And I know that you were taught this in algebra. You might have forgotten it though. And the reason I know that you were taught it in algebra is I'm currently teaching it in algebra. Actually, I was doing it last Thursday and Friday in my Algebra 1 classes. So exponential functions, okay? Um, First off, you've probably heard of things that have grown exponentially, okay? You might have heard that expression, but you might think, well, what does that mean by exponential? I mean, exponential for the most part, it means like something starts off really, really slow and then it eventually takes off really, really fast, okay? Like sometimes populations grow exponentially, like rabbits, okay? You have a few rabbits, then a few more rabbits, and a little more, and then all of a sudden, bam, it just explodes, okay? There's just a whole bunch of rabbits, okay? And they can also, things can decay exponentially, okay? Like for example, radioactive material. You might have heard of things like called half-lives. Like the half-life, like if you have a radioactive substance, I'm not a chemist here, okay, so this may not be totally accurate, but I know that over time the radioactive substance breaks down. So like a half-life of something means how long it takes for half of it to go away, okay? And it might be like after the certain half-life, a bunch of it goes away, and then, well, think about it this way. If you have a substance, say you have 100 pounds of some substance, well, the half-life might be a year. So what they're saying is in a year, half of it will be gone, like 50 pounds will be gone. Then a year later, half of that will be gone, so 25 pounds will be gone. And a year later, half of 25 pounds will be gone, okay, which is 12 and a half pounds. So it takes, there's a lot, and then it dwindles down. Like, for example, it lost 50 pounds, then it lost 25 pounds, then it lost like 12 pounds, then it loses 6 pounds. It's losing less and less and less, okay? So those are examples of exponential functions, okay? I'm going to give you some examples of exponential functions, and if it was me, I would just watch, okay? I would just watch on these, and then maybe write some stuff down. If I gave you something such as this, if I gave you 3 times 2 to the x power, that's an exponential function, okay? I didn't tell you why yet, okay? If I gave you this right here, 1/4 times 4.7 to the x, that's an exponential function. If I gave you negative 8.3 times 5/8 to the x power. Okay, that's exponential. Now, examples of things that are not exponential would be something like this. Okay, if I gave you 7 times x squared, or if I gave you, now, real quick here, any idea why, I mean, exponential, I mean, the first few letters of exponential is exponent, okay? It's got to have an exponent. Well, kind of. It's got to be more. Say it again. The exponent's got to be x, okay? It's got to be raised to the power of x. Now, if I switched these and made it 7 to the 2 times 2 to the x, then it would be exponential, okay? So the exponent's got to be an x, okay? Now, that's not good enough, though, okay? I hope we said exactly what I was hoping for. That's great so far, okay? But if I give you something like this, 9.6 times 1 to the x power. That is x for an exponent. It's not exponential, though. And the reason is, what's raised to the power of x can't be 1. It can't be 1, and here's why. If I was to plug in values for x, okay, first off, do we times first or do powers first? We do powers. If I plug in 1 for x, 1 to the first is 1, times 9.6 is 9.6. Plug in 2 for x. 1 squared is 1, times 9.6 is 9.6. If I plug in 4 for x, 1 to the fourth is 1, times 9.6 is 9.6. It's always 1 to any power is always 1, okay? So it's not exponential, it's not growing at all, okay? Or it's not going up or down, okay? So this can't be a 1. What if I gave you this? 2/3 times negative 5 to the x. That's also not exponential. And the reason is it can't be a negative base. It can't be, okay? What's that?
It doesn't get it bigger.
Well, here's what happens. If I was to plug in 1 here, negative 5 to the first is negative 5. Times this number would be a negative number. It'd be a negative number. If I plug in 2, negative 5 squared is positive. Times a positive is a positive. And if I plug in 3, 5 to the negative third is a negative number. It would go negative, positive, negative, positive, negative, positive. So is it getting bigger or is it getting smaller? It's kind of doing both. It's kind of like this. If I gave you these numbers, 1, negative 2, positive 4, negative 8, positive 16. Any guesses what the next number is going to be? There's a pattern here. Anybody see it? 1, then negative 2.
Positive 64.
Positive 64.
Just keep jumping over there.
Then negative.
Well, but there's a pattern. What's a pattern? What are we doing?
You're doubling and,
Changing the sign.
yeah.
So basically, I'm timesing by negative 2. So the number's getting bigger or are they getting smaller? Well, they're going back and forth. A small positive number, a bigger negative number, an even bigger positive number, even bigger negative number. I mean, it's getting big number, really small number, then positive. I mean, it's going back and forth. You can't say it's getting bigger or smaller. It's fanning out in both directions, okay? So you can't have a negative exponent. I'm sorry, you can't have a negative base. You cannot have a negative base. So I always said it's got to be the power of x, and that's right, okay? Or if I even just gave you something like this, 2 to the x. That's exponential, okay? Now, another thing, I thought you could have times something. Well, I could put times 1, and that doesn't change things. When you times by 1, nothing happens, okay? So your exponent's got to be an x, and your base cannot be 1 or negative. Or it can't be 0 either, okay? If your base is 0, it's just going to all be 0, okay? Now, there's two different types of exponential functions. There's exponential growth, and there's exponential decay. Growth means it gets bigger, decay means it gets smaller. These two, this one right here is growth. I didn't tell you why. This one right here is growth. This one right here is decay. This one right here is growth. Any idea why this third one's decay?
There's a negative up front.
Say it again.
There's a negative up front.
Oh, still decay. That's a good guess.
Times by a fraction.
Be careful when you say a fraction. If I make this, it's still a fraction, but it's growth now.
You're timed by something less than 1.
It's a fraction smaller than 1. It's got to be less than 1, okay? Because think about it. When you times by 1, nothing happens. What happens when you times by a number bigger than 1?
Gets bigger.
Gets bigger. What happens when you times by a number smaller than 1? Gets smaller. It gets smaller, okay? All right. So that's what you need to look at is this right here. The number that you're raising, the base. What you're raising to the power of x is bigger than 1. It's growth. If it's smaller than 1, it's decay. All right? So here's what I would jot down if it was me. If you haven't, I said, just watch for a few minutes and then maybe take some notes. I would jot this down. I mean, unless you're sitting there going, I'm not going to forget this. Bless you. Okay. Has to be of the form a times b to the x power, and b is not equal to 1, and it can't, and also b has to be bigger than 0. Okay? It can't be 1, and it can't be negative. It can't be negative, okay? And if b is bigger than 1, it's growth. If b is less than 1, it's decay. That's the mathematical way of saying what all those examples right there, okay? It's got to be some number times some number to the power of x. Your base can't be 1, and it can't be negative. It's got to be bigger than 0. And if it's bigger than 1, it's growth. If it's less than 1, it's decay. And I'm glad Iobi said what he said here, okay? He said a fraction. If b is a fraction. Got to be careful. If I gave you 7 times 4/3 to the x, would that be growth or decay?
Or no, growth.
Growth, because 4/3 is
Is
bigger than 1. 3/3 is 1. 4/3 is bigger than 1. Now if I made it 4/31, now it's decay. Because 4/31 is less than 1. Okay? All right. Now, and what I want you to understand is this. Exponential functions look sort of like this. Growth functions look sort of like this. Okay? They start off really slow, and then they take off. Decay, and they never hit the x-axis. Decay functions go like this. Okay? Now, when we're doing these graphs on your next test that you'll take in about 3 or 4 weeks, whenever it is, I'm not sure exactly when, I just want really quick rough graphs, okay? Now, when I say rough graphs, not that I want to get you, but be careful. If you do something like this, if I see a graph of an exponential function and you do this, I'm going to take points off. Any idea why I would take points off on that? It's close. Yeah, it doesn't swing back up. It gets really, really, really close to the x-axis, but it doesn't touch the x-axis, okay? Or, don't do this. I'll see this a lot. Don't do this. It's every year I say, don't do this, and I always have at least one person that does it. They'll do this. I'm not a good drawer, but that's god awful, okay? And I'm going to be very careful on how I say this. Why do you think that's a really bad drawing of that function?
Because it goes up.
There's a key word that I said there. Why is that a really bad drawing of that function? That's not a function. It fails a certain test. You guys remember that test?
Oh,
Vertical line test. If this goes straight up and down,
the line.
it fails the vertical line test right there. It better not look like a right angle. That's terrible, okay? Even though it looks pretty, that's not right, okay? Or don't do this. What's wrong with this one? It didn't just touch the x-axis, it touched it and went under it, okay? Doesn't do that, okay? There are exceptions, though. If I give you this right here, y equals 2 to the x, and we're going to graph some of these maybe today, looks sort of like this. But if I had 2 to the x minus 5, what would that minus 5 do to the graph? We've done this in September.
Take it down.
Drop it 5 spots down. So, in this case, it would look like this. It does touch the x-axis, but it doesn't touch the line y equals -5 because it dropped it down 5 spots, okay? I'm going to learn you a new word here, okay? When it gets very, very, very close to that, that looks like a boundary. That boundary is called an asymptote, okay? An asymptote is a boundary that something gets very, very, very close to, okay? The example I use is this. Let's say I'm going to walk from this side of the room to the other side of the room. And let's just say it's 40 feet. Okay, I don't have any idea how long, that's probably too big, but let's just say it's 40 feet. If every day I walk half the distance, you gotta be careful on this. Every day I walk half the distance, how long would it take before I get to the other side? Some students say, oh, 2 days.
You would never.
Theoretically, I'd never get there. Now, some people think 2 days. You walk 20 feet, 20 feet. That's not what I'm saying. I'm saying I walk half the distance, so I walk 20 feet. The next day I walk half that. How many feet are left? 20.
20.
So I walk 10 feet the next
He
day.
only-
Then I walk 5 feet. So every day I'm walking, but I'm walking less and less and less. I'm only walking, theoretically, I'd never get there, okay? The reason is, okay, another way of saying is every day I walk half the distance. Another way of saying that is every day I keep half the distance between us. Well, if I'm always keeping some distance between me and the wall, I never get there, okay? I never get to the other side. Now, realistically, I get there because if I get like a trillionth of an inch away to the wall,
You're pretty much.
I mean, you can't measure a trillionth of an inch. You can't. Now, how do you walk a trillionth of an inch? You can't. Human beings are not. We can't do that. We can't move that little. Okay. So and what else I want to say this? So that would be something called exponential decay. I'm getting close. It's getting smaller and smaller and smaller. That wall would be an asymptote. Okay. That would be an asymptote. It's a boundary. I never get to that wall. Okay. So anyhow, a boundary that you get very, very, very close to is called an asymptote. Okay. Throw one more example to you guys that I told just last week to my Algebra 1 classes. I don't know if it's a true story or not, okay? I heard it once, whether it's true or not, it doesn't matter though. An example of exponential functions is this. Supposedly, 1,000 years ago or something over in England or somewhere over in Europe somewhere, there was a king. And he had a daughter, a princess, and she was in major harm's way or something like that, and a peasant saved her life, okay? This peasant, this ordinary guy saved her life. The king was extremely grateful, very grateful to the peasant for saving her life. So he brought the peasant up before him and says, okay, I tell you, whatever you want in my kingdom, I'm going to give it to you. And the peasant's like, okay, well, you know, what the heck? I'm not a greedy man. He saw a checkerboard or a chessboard off to the side, and he's like, you guys know how many squares are on a chessboard or a checkerboard? Anybody know? 64 squares. He said, I tell you what, just take the pieces off the chessboard, and just on that very first square, put a penny. Just put a penny on the first square. He said, and every square after that, just put twice as much on each square after that. He says, whatever's on the board, I'll just take that. The king's like, okay, no problem. So, king puts a penny on the first square. Second square, he puts 2 cents. Third square, he puts, now careful, doubles it, 4 cents. Fourth square, he's had 8 cents. Fifth square, 16 cents. Oops. 16 cents. Now the king's going, whatever. I mean, this guy just wants change, not a big deal. It adds up. We'll see what happens when it adds up. Sixth square is 32 cents. Seventh square is 64 cents. Eighth square is $1.28. We're going to make it $1.25 just to make it easier. Okay? Ninth square, double $1.25 or $2. So we're at like, now I just want to make sure you understand. So are we saying that He has 2,050 cents. He has 250 plus everything above it, okay? 10th square is $5. 11th square,
And this just goes on 54 on.
yep. 13 is 40. 14 is $80. 15 is 160. 16 is 320. 17 is 640. Double 640 is 1280. I'm gonna make it 1250, just to make it easier. $2,500. 20 squares is 5,000. 21 squares is 10,000. 22 is $20,000. 40,000. 24th square is $80,000. 25th square is 160,000. 26th square is $320,000. And again, he has 320,000 plus everything in front of that, okay? And just so you want you to realize is this. On the 4th square, how much money is in front of the 4th square? 3 cents. Almost the same as that. How much is in front of the 16 cents? If you add these up, it's 15 cents. It's basically the same. Every square in front of it is almost the same amount, okay? So if he has $320,000 just on the 26th square, how much is everything in front of that? Another $320,000, okay? $640,000. We're over $1 million. How many squares are there? 64. Now I want to make sure you understand. So are we saying that, like for example, let's do this, 28, 29, 30, 31, let's see if I can get this. 128,000 or 1,280,000. I'm going to make it 1,250,000. 2,500,000. 5 million. 10 million. 20 million. We're halfway there, and he's at 20 million. Now, I just want to make sure you understand again. So on the 32nd square,
He's got 40 billion.
he's halfway there. So to find out on the 64th square, do I just double this?
Yeah.
No.